Hello. A new day, a new derivative. Let's hit it. Okay, so we've got to take a look at taking derivatives of parametric functions, or functions when they're defined parametrically, because there's a little twist when they're defined parametrically. So if you don't know what I'm talking about when I say a parametric function, you should be watching the two videos that came before this that are posted in Edpuzzle that talk about just a quick introduction to parametrics and then a little bit about graphing and dealing with parametrics. But just as a quick kind of review of what parametrics are, parametric functions are functions that are defined in terms of time. So they're used a lot in motion. They're used a ton in physics in motion. So basically what we have is, instead of just y in terms of x, we have two functions, one that expresses x and one that expresses y, both in terms of time. So at any given time, you can give a pair of coordinates, x and y. So parametric functions, parametrically defined functions, aren't just one equation, it's two equations, an x of t and a y of t. So often we see something like this. So in this case, our x coordinate is given by t minus 5, and our y coordinate is given by 0.5 t squared minus 9. So at any given time, its x position is going to be that time minus 5, and its y position, or its vertical position, is going to be given by that time squared, half of it, minus 9. So because we have those two equations, we're able to make a table of values for a parametric function, and we're able to graph. When we plot those points, we're able to graph the path of the object, because again, these coordinates, the x and the y coordinate, are going to give me its position at any given time. Okay, so if you take a look at this particular parametric function, the x position at any time is given by t minus 5, so it's pretty easy to fill in the x coordinates for this function. At negative 5, it's going to be negative 10, and then it's just going to negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, right? This is a linear relationship. For the y values, I'm going to have to square this value, cut it in half, subtract 9. So I'm going to start at the easy one, which is 0, right? Whoops. At 0, it's 0.5 t squared, so it's 0 minus 9. And then since this is a parabola at minus 9, I know I'm gonna have symmetrical points around here. So if I do 1, that is 0.5 minus 9, so negative 8.5. And I know I'll have a negative 8.5 on this side as well. When I do 2, that is 2 squared is 4, half of that is 2, so I'm going to have a negative 7 on either, for both positive and negative 2. When I do 3, it's 4.5, so 3.5. Right? No, that's 4.5. Oh my. Okay, and then when I square 4, 16, 8, so you get negative 1, and when you square 5, 25, 12.5, you get 3.5. There we go. Okay, so again, once you have those values, at each time, I now have a coordinate. I can tell you where it is. Okay. What's interesting about parametrics that I think people always find a little bit unnerving, if you will, is that you have these values for time that you were given, but when you go to make the graph, time is nowhere to be found. Right? It's this third dimension that we don't see. Right? So the time is what got us our values, but when we actually make our graph and plot our points, time is nowhere to be found. So I actually can't graph until I get to negative 1, because I don't have enough space on my grid. So at time equals negative 1, I'm at negative 6, negative 8.5. So somewhere down here. And then at 0, I'm at negative 5, negative 9, negative 4, negative 8.5, negative 3, negative 7, and -2, -4.5. So you can see that you get this little swoopy curve. And I did a terrible job at graphing it. You can see that as well. But if you look here, the way the points go, the idea is this, that as time passes, you can see this was what? This was t is -1, 0, 1, 2, 3. And so if I kept going, we would get this. In the video that I showed you, he puts the arrows on it to show that this is the direction of the path. Now in this particular graph, it doesn't like loop back around on itself, but sometimes parametrics can do that. Like they can go this way and then loop back around and swoop out. So we can get some pretty cool graphs that aren't necessarily functions. They're not functions y in terms of x, but they could be parametric functions. I like to use air quotes for that. Okay. So what we need to look at is parametrics and calculus. And frankly, you don't really have to know a whole heck of a lot about parametrics to do the calculus with parametrics. We're going to do their derivatives, but the first thing I want to show you is the notation. So sometimes they give us the equation written as x of t and y of t, right? And that's nice. So sometimes, so I have it written here as a heart in a cloud because I just want to show you how it shows up for us. There's another notation that they can give us, which is called vector form. And if you're in physics, you may have seen vectors before and you know vector notation. If you're not, and this is new, it's just once you see it, you'll know it's fine. All right, so vector form, you have two options. You can either write it using the greater than or less than signs. I like to call them the pointy brackets. I think it's easy to remember that this is the vector notation because these are also little v's. But you don't want to use like rounded regular parentheses because then it's going to look like an ordered pair or something, right? So it's a vector. You just put the x equation first and the y equation second. The other way to do it is to use what's called IJK notation. IJ and K are called unit vectors. I is the unit vector in the x direction. It means I is like one step in the x direction, J is one step in the y direction, and K is one step in the z direction, which is out of the board, which we're not going to touch. That's physics. And so sometimes they will write vectors and it looks like a goofy equation with extra variables in it, but it's just another way of saying here's the x coordinate and here's the y coordinate, or here's the x component and here's the y component. It looks like this. Oh wait, I'm sorry. That's the example of vector notation. I'm really killing it. Here's the IJK notation. Okay. Notice that these i's, this is literally read I hat and J hat. Like they're wearing little hats. I think of them again, they're little V's, they're little upside down V's. So this just means in the x direction and this means in the y direction. This is, so there's, if it's given to you like this, then you know this is your x of t and this is your y of t. If you need to write it like that, then you literally just take these equations and put an I after the x and then J after the y. So it looks like that. I would very highly recommend putting them in parentheses because, after all, this I applies to that whole equation and this J indicates that this whole equation is the y. Okay, so again, it's nice if you see it like this, but don't be thrown off if you see it in either of these ways. It's just another way of writing it. It doesn't really matter how you give your answer, but if it's handed to you like this, then you need to make sure you understand the notation, right? It's just like seeing y prime versus f prime of x versus dy dx. It's all the same. It's just you have to know what you're looking for as far as notation. Okay, so derivatives. Okay, a parametric function is going to have a derivative as long as both x of t and y of t have a derivative. So the derivative, as you'll see in a minute, is a combination of the two derivatives of the pieces, right? So x of t has to have a derivative and y of t has a derivative. So if you have a parametric function, for example, where x of t is like an absolute value function, at the point where x of t doesn't have a derivative, then the whole parametric won't have a derivative because the parametric can't have a derivative if either one of its pieces doesn't have a derivative at a point. Okay, so we say it's differentiable if it's differentiable at every t value. In other words, there can't be any times at which the derivative fails to exist. So It's the same as rectangular coordinates, x and y. It's just that instead of it needing to have a y value for every x value or a derivative at every x value, now our variable is t. So there can't be any t's that cause problems. Okay, it's considered smooth if both of the derivatives are continuous. And we'll talk more about that later, but continuous derivatives mean that the slope exists at every point, and this is really important. It can't have you can't have both components of your parametric, the derivatives, be 0 at the same time. So if x of t is 0, that's fine. If y of t is 0, that's fine. But if they're both 0 at the same time, that's a problem, and you'll see why that is in a moment. All right, so I want to show you where this formula comes from so that you're not memorizing. I hate memorizing. All right, so remember that when we're talking about parametric functions, we are talking about an x-coordinate written in terms of t and a y-coordinate written in terms of t. So, sorry, I didn't mean to do that. Don't look. All right, so if I take the derivative of this x equation, it's going to be the derivative of x, but it's the derivative of x with respect to time, because the equation is written in terms of t. What we're used to seeing in rectangular coordinates, what makes us feel happy, is we see like a y that's written in terms of x, right? And because of that, it's a y written in terms of x. The derivative is the derivative of y with respect to x. When we first learned this notation, I said that a lot of people really don't. At first, you're like, what the heck is that notation for? It's ugly, like let's just use y prime. This is one of the spots where I think that this notation is really, really helpful because it gives us more information. What we know, if I just wrote x prime, that doesn't really tell a story of the derivative as much as if I write dx dt. If I write dx dt, that's telling me this expression you're about to see is a derivative of x, but it's with respect to t. In other words, t was the variable, and that's important. Okay. If I take the derivative of y, I'm going to get dy dt. Here's the problem. The slope of a graph is defined as a change in y over a change in x. And that hasn't changed. Just because you defined your function differently, just because you defined your function parametrically, in terms of one equation for x and one equation for y, doesn't change the definition of slope for all eternity. That the slope of a graph is between 2 points is a change in y over a change in x. So in order to find dy dx, I've got to find a way to combine these two and get that t out of there, because what I need isn't a dx dt or a dy dt. When I go to my graph, there's no t, it's just y's and x's. So I need to eliminate that t. I need to eliminate the parameter. Okay? And here's how we do it. It's pretty darn tricky. If you want dy dx, all you have to do is take your dy dt expression and divide it by your dx dt expression. And again, here's where this notation is handy, because you can think of dy dt not just, or I'm sorry, dy dx, not as just notation, but as individual pieces that mean something, right? dy is a teeny tiny change in x, or y, jeez, and dx is a teeny tiny change in x. So all this is a delta y over a delta x. It's change in y over change in x. Okay. This is a change in y over a change in t. This is a change in x over a change in t. And they're all infinitely small. So if I write it out like this, and I think of these all as individual quantities, look what happens algebraically. They cancel. In other words, you could rewrite this. I know everybody loves a fraction and a fraction. You could bring this denominator and do an invert and multiply, right? So instead of writing it as a quotient of two fractions, you could rewrite it as a multiplication and make this dt over dx. And look what happens. The dt's cancel. In other words, the change in time poofs out, and what we're left with is this nice quotient that just happens to be change in y over change in x, the slope of the graph. So if you want the derivative of a parametric function, all you have to do is take the derivatives of these individually and then divide them out. dy dt over dx dt. Remember, you want dy dx, so you put the y on top, put the x on the bottom. The dt's algebraically cancel out, and we're done. So in order to find derivatives of a parametric function, you have to take two derivatives and then put them in a quotient. All right, let's do it. So here we have a parametrically defined function. X is t squared minus 5, y is 2 sine t, and they give us an interval of time between 0 and pi. And here's the graph of this thing. So notice that when time is 0, my x value is -5, and my y value is 0. In other words, at time is 0, this is where we are right here. Here's our starting point. Okay. Oh, goodness. Okay. So let us, it says rewrite the parametric function in both vector formats. I'm going to have to do a lot of erasing on this slide to have room to do everything. Okay, so here's my x and here's my y. So if I want to write it in my vector formats, my pen. Okay. The first one being the one with the little pointy brackets, right? I'm just going to put my x equation, t squared minus 5, comma my y equation, 2 sine t, and close my pointy brackets. Okay. Or I could do it in IJK notation. So I'm going to put t squared minus 5 in parentheses with an I hat, and then I'm going to put my 2 sine t in parentheses with a j hat. Right? That's it. This, and this all mean the same thing. They all mean your x equation is t squared minus 5, your y equation is 2 sine t. Okay. So the next three questions are talking about the slope of the tangent line. So if I want the slope of the tangent line, we know that that means we need dy dx. Okay. And we know that dy dx for a parametric comes from taking dy dt and dividing it by dx dt. Okay. So you could just write out that whole formula, right? And we will do that here in a minute. But when they ask you questions here, like number 2 and 3, at what point is the tangent line horizontal and at what point is the tangent line vertical, you really only have to work with one piece at a time. If you want a horizontal tangent line, then that means that your slope, your dy dx, has to be 0. In this case, that means that just your numerator, or your dy dt, needs to equal 0. I don't even need to worry about what dx dt is, unless it's also 0. We'll talk about that. All right. So if I want a horizontal tangent line, I need this numerator to be 0. I need dy dt to be 0. So I'm going to take my derivative. Dy dt is 2 cosine t, and I say, well, when does that equal 0? That's going to equal 0 when cosine equals 0. Right? And when does that happen? On this interval, cosine is only going to equal 0 one time, and that's at pi over 2. So at t equals pi over 2. That must be up here somewhere. So the only thing we have to do is verify that my x value isn't also going to be 0 at that point. So I'll find my dx dt and make sure it's not also 0. I'm going to use dx dt to answer number 3 as well. So dx dt in this case is just 2t. So I know I will have a horizontal tangent line when dy dt is equal to 0. That's going to happen at pi over 2. So all I have to do is double check and make sure that my dx dt isn't also going to be 0, and it won't be. Now think about this. If this numerator is 0 and this denominator is 0, that's what we learned back in the day. It's called an indeterminate form. Right? So we'd be in trouble. That's why they can't be 0 at the same time. Okay. Now AP doesn't often throw that at you. I can't see them throwing that at you, but they will hit you if you don't check, right? So if they say, when does it have a horizontal tangent, then we're going to say when dy dt is equal to 0, but dx dt does not equal 0. So you have to kind of make sure you state both things. So in this case, that's at pi over 2. And I would like you to note here that on this graph, you see there's a horizontal tangent here, right? But again, look where it is. That's not pi over 2, right? Because pi over 2 is the time. This point right here, it's going to come from these at pi over 2, right? So if I want the point, I know that's when t is pi over 2. So I need to put pi over 2 into here. So my x-coordinate is going to be pi squared over 4 minus 5. And my y-coordinate is going to be 2 sine of pi over 2, also known as 2. So look, this x value right here is pi squared minus 4, or divided by 4 minus 5. And this y value is 2. So this is giving us the coordinate. This just gives us when it happens. You're not going to see this pi over 2 in the graph. Okay. This is the when, this is the where. All right, so if I want a vertical, then instead of let me write this again, hold on. dx dt was 2t. dy dt was 2 cosine t. Right. So if I want a vertical tangent, that means my denominator has to equal 0. In other words, my dx dt has to equal 0. Well, that's not very tough to do, right? So I have dx dt is 2t. So that's going to happen when time is equal to 0. At 0 seconds, I'm going to have a vertical tangent. Well, we already actually did that point. That's one of the first things we looked at. At 0 seconds, my x-coordinate is -5, and my y-coordinate is 0. So over here, right at the beginning, that's where I see my vertical tangent. And again, you're not going to see this when in the graph. This is the graph of position. If they say at what point, and you stop at t equals 0, you have not answered the question. That's the when it happened. It's not the where it happened. Okay, again, we better verify we don't have a 0 for y as well. So let's just check quickly and ensure we don't. Okay. So, I'm sorry, I pointed to the wrong thing. You put a 1 in, or I'm sorry, a 0 in here, you don't get a 0. Okay. All right. Last part, number 4 here. Once again, I am going to write these derivatives because I just keep erasing them. dx dt is going to be 2t, and dy dt is going to be 2 cosine t. So if I want to find the slope of the tangent line when t is equal to pi over 3, again, I need dy dx, and I know that dy dx is just going to be the quotient of these two things. So my dy dt on top, so my 2 cosine t on top, and then my dx dt, or my 2t on the bottom, and those cancel. And I need to evaluate that at pi over 2. So the first thing I'm going to do is plug pi over 2. I'm just going to plug pi over 2 into here and go from there. So on top I have the cosine of pi over 2, and on the bottom I have pi over 2. Now, piece of advice. On the AP, they said find the slope when t is pi over 3. Oh my. I'm over here giving people advice, and I wrote pi over 2 instead of pi over 3, so guess whose answer was wrong? Mine. I was just about to say don't simplify it, because if you mess up your unit circle, then you'd miss the answer point, and I would have missed the answer point anyway just because I don't even know how to read the question. Okay, so I'm evaluating at pi over 3 because that's the time they gave me. So cosine of pi over 3 over pi over 3. Now, again, if you don't have to simplify this, as Brian Passwater says, let us believe that you know your unit circle and that you just were trying to save time. Let us live our lives believing that. Okay. If it's multiple choice, or if your teacher is mean and you have to simplify it, then of course the cosine of 3 is, that's right, it's 1/2. So I would have 1/2 divided by pi over 3, and then let's see if we cannot mess that up. So that would be 3 over pi. So that would be 3 over 2 pi is my slope at that point. Lots of little mistakes you could make in there with inverting and multiplying and fractions and all that good stuff. So it probably is safest, again, on the AP. It sounds so silly, but it is safest to just leave it. A lot of times in a rush, we tend to make little mistakes. So just leave it. Okay, so that last question we did is kind of the way we see it when they try, we see a lot of open-ended questions like that where they ask us multi-parts. But sometimes they just ask us a straightforward, hey, give me the derivative of this parametric function. Again, in that case, I am literally just taking dy dx dy dt over dx dt. So dy dt in this case, y dt, derivative of tangent is secant squared. And the derivative of my secant is secant t tangent t. And this simplifies a little bit. One of these secants cancels with this secant, and you end up with secant t over tangent t. And actually, secant is 1 over cosine, and tangent is sine over cosine, so this turns out to be 1 over sine, also known as cosecant. What? So again, this is a perfectly fine answer right here, right? Secant squared t over secant tangent. That's a correct answer. But there's a lot of simplifying that can be done here. And any of these answers, any of these kind of interim things would be all right as well. Okay. Going to do that one. That's a little bit much for now. All right, so I want to show you what happens with higher order derivatives of parametrics. There's a little twist with higher order derivatives of parametrics. So it's not terrible, but I want to show you kind of like where it comes from. So if I give you a parametrically defined function, so x of t here, we have t cubed plus 5t, and y of t is e to the 4t. And I want the second derivative. For rectangular coordinates, x and y, if I had y in terms of x, I would just take two derivatives and call it a day, right? I would have a pretty easy, that's a pretty easy question for us. Parametrics, it's not that simple. Here's why. When you take the derivative, dy dx, of this function, you take the derivative of your y, you get 4e to the 4t. You take the derivative of your x, you get 3t squared plus 5. Okay. If I go to take the derivative of that, it's not the same as when I take second derivatives of rectangular coordinates, and here's why. When I have rectangular coordinates, and this looks like a lot, but kind of just bear with me for a second. If I want a second derivative, what I'm doing is I'm taking my first derivative, which is in terms of x, right? And I'm taking the derivative of it again. So it's a d dx. So if I ask you to take the second derivative of, say, oh, I don't know, x cubed, you're going to have a 3x squared in here. So when you take the derivative of that, it's a derivative with respect to x because the variable of the thing in here is x. And again, I go back to this idea that this is more than notation. This is giving us more information. This says, I took the derivative twice, right? I took dy dx and I took the derivative of it again, and I did it with respect to x. That's important because that is not what's going to happen over here. If you take the derivative of this, it's not going to be this. Because if you take the derivative of this, what you have is a derivative with respect to t. If you take the derivative of this, you're taking your dy dx. But in this case, your dy dx is in terms of t. So when you take the derivative of this, which we are going to do, it's a quotient rule, you're not getting d squared y over dx squared. Not getting that. You're getting this. I took dy dx and I took the derivative of it with respect to t. So thinking about these little guys as individual quantities, what I have now is a second derivative, but the first derivative I took was in terms of x, and the second derivative I took was in terms of t. So notice that this denominator does not line up to being a dx squared. That's a problem. We have to fix it. The good news is it's an easy fix. Okay, so if I want a second derivative, it's fine if you're in rectangular coordinates, you take the derivative again. As long as the first time you took the derivative it was in terms of x, and the second time you took the derivative it was in terms of x, you're good to go. You got a second derivative. But as soon as you get this third variable kicking around, the first time you take the derivative, you're doing it with respect to x, right? You do the quotient, and the t's cross out, and you get a nice, neat dy dx. But when you take the derivative of that, you're no longer doing a derivative with respect to x, you're doing a derivative with respect to t, and this is what you have left, and we have to fix it. You cannot stop there. Okay, it's an easy, easy fix. So here's what I want you to look at. And again, think about these individual quantities. What I have is a second derivative. The first time I took the derivative, I took it in terms of x. The second time I took it in terms of t. What I want is d squared y, second derivative, and I want 2 dx's down here. In other words, literally think of this as I took the derivative with respect to x, and then I took the derivative with respect to x again. Okay? I need to take this, which is what I'm going to have when I use the quotient rule and take the derivative, the second derivative of this, and I need to turn it into what I want. Algebraically, there's one little thing I could do to fix this. How do I turn this into this? Well, what I need to do is replace this dt with a dx. So watch this. If I multiply by a dt over dx, wouldn't that get me what I want? These dt's would cancel, and you'd have a dx and a dx. Okay. Now, that would get me what I need, right? This is not what I need. This is what I need. All right, so here's what we're going to do. To get our second derivative, I'm going to take the derivative of my first derivative. I'm going to take this derivative up here. This is my first derivative, and I'm going to take its derivative. But then I won't be done, because once I do that, I'm going to be here. Whoops. This might be my best video yet. Once I take the derivative of this with respect to t, that's going to put me here. I need to do this little fix to get me where I want to be. Okay, and that is divide by dx dt. Okay, so let's go do this, right? I'm going to take this box out of the way so that we have some space to do the problem. All right. When I go to do this derivative here, it's a quotient rule. Remember, those things don't go away just because we're doing other derivatives. So when I go to do this derivative, it's going to be 3t squared plus 5 plus the derivative of my numerator. So I have to chain rule again there. So it's going to be 16 e to the 4t minus my numerator times the derivative of my denominator, which is 6t, all over my denominator squared. So 3t squared plus 5. Now, remember where this came from. This derivative up here. This is dy dt over dx dt, right? So this right here, that's my dx dt. So I need to divide by dx dt. I'm going to write it as this, because I really don't want to do a fraction. I really don't want this to be a numerator of a new fraction. So all I have to do is multiply by 1 over dx dt. That's the same as dividing by dx dt. So I'm going to make this a 3t squared plus 5. And there's my whole big answer, right? In the end, what you could do is just pop a little squared on there, right? So you have this numerator, and then you have this denominator multiplied by, oh, this should be a squared anyway, sorry. And then multiply this in, and it would be a 3t squared plus 5 cubed, because you have a new one now. All right, so I know that was a lot. That was a lot of talking. I know, because I got interrupted 1,000 times. This really It doesn't really become a huge deal. I hate to say that. On the AP, we'll see a couple parametric functions. Sometimes we get an open-ended on parametrics, but we have more work to do with parametrics later, and we will revisit them. So I just wanted to show you quickly how to do derivatives of them, and then when we get into our next unit, we'll have to talk about doing integrals with them. But parametrics are one of the topics that distinguishes A, B, and BC. So there are only a few of those things. And so we are always guaranteed to see not necessarily all of them, but we almost always see either a parametric problem or a polar problem, because those are two things AB doesn't do that we do. I would prefer parametrics to polars, but that's just me. So we'll talk about polars later. But I just wanted to give you a quick overview of derivatives of parametrics so that we have that in the bag, and I promise, I know you're super excited to revisit parametrics in the next unit, but we will. All right, make sure you put any questions in the end here, and I will answer them when we get together again. Bye.